Hello, my dear students. Welcome to IKSR chemistry classes. Here we are in lecture number 4 on ESR spectroscopy, which is an important topic in inorganic spectroscopy. Questions related to this chapter are asked frequently in competitive such as NET, GATE examinations as well as general examinations. Representation of ESR spectrum. The ESR spectrum is represented in two forms. The first one is as absorption signal and the second one is as derivative signal. Let us see how absorption signal and derivative signal can be obtained. The absorption signal is obtained by plotting absorbance of electromagnetic radiation against the applied magnetic field. If absorbance is plotted against applied external magnetic field, the signal obtained is called absorption signal. On the other hand, the derivative signal is obtained by plotting dA by dV against the applied magnetic field. If dA by dV is plotted against external applied magnetic field, the signal obtained is called derivative signal. Let us illustrate absorption signal and derivative signal with the help of a diagram. Here in the first figure, absorbance is plotted against applied magnetic field. The signal obtained in this way is called absorption signal. On the other hand, if dA by dV is plotted against external magnetic field, the signal obtained is called derivative signal. It is one absorption signal and here also it is one derivative signal, not two signals. It is one derivative signal. On the other hand, it is one absorption signal. A standard in ESR spectra. For obtaining ESR spectra, that is electron spin resonance spectra, the sample must be in the form of a single crystal, solid powder, liquid or solution. The sample whose ESR spectrum is to be scanned should be present in the form of a single crystal, solid powder, liquid or solution. Diphenyl picryl hydrazine, abbreviated as DPPH, is generally used as a standard in obtaining ESR spectra. It means diphenyl picryl hydrazine is the standard, is the reference plotting ESR spectra. And this compound diphenyl picryl hydrazine occurs completely in the form of free radical. Number of unpaired electrons in 1 gram diphenyl picryl hydrazine. The structure of diphenyl picryl hydrazine is given here. It is nothing but diphenyl, two phenyl groups This is picryl group and hydrazine, diphenyl picryl hydrazine, which is abbreviated as DPPH. It contains one unpaired electron and it occurs completely in the form of free radical. Let us calculate the number of unpaired electrons in 1 gram of DPPH. The molecular formula of DPPH is C18H12N5O6. On this basis, its molar mass has been calculated to be 394 gram per mole. Number of moles in 1 gram DPPH will be equal to 1 divided by 394. This is number of moles present in 1 gram diphenyl picryl hydrazine. And in order to get the number of molecules, it must be multiplied by Avogadro's number. The number of molecules in 1 gram DPPH will be equal to 6.022 into 10 to the power 23 divided by 394. It is the number of molecules present in 1 gram DPPH. It is obvious that one molecule of diphenyl picryl hydrazine contains one unpaired electron, and therefore the number of unpaired electrons in 1 gram DPPH should be equal to the number of molecules present in it, and therefore the number of unpaired electrons in 1 gram DPPH will be equal to 6.022 into 10 to the power 23 divided by 394. This quantity can be written as 602.2 into 10 to the power 21 divided by 394. On dividing 602.2 divided by 394, we get 1.53, and this is 10 to the power 21. Thus, the number of unpaired electrons in 1 gram DPPH is nothing but 1.53 into 10 to the power 21. This number of unpaired electrons is present in 1 gram diphenyl picryl hydrazine. Now, let us see sensitivity in ESR spectroscopy. We have already discussed in the earlier videos that ESR spectroscopy is more sensitive. ESR spectral technique is more sensitive than NMR spectral technique, and it has been illustrated in detail. About 10 to the power minus 9 gram of diphenyl picryl hydrazine can be detected by ESR spectra. This very small amount, 10 to the power minus 9 gram of DPPH, can be detected by ESR spectra. We already know that we have already calculated that 1 gram of DPPH contains 1.53 into 10 to the power 21 unpaired electrons, and therefore it means about 10 to the power 12 unpaired electrons. This multiplied by this one is about 10 to the power 12 unpaired electrons can be detected by ESR spectra. If the number of unpaired electrons is less than 10 to the power 12, they cannot be detected by ESR spectra. But if the number of unpaired electrons in a given sample is equal or greater than 10 to the power 12, they can be detected by ESR spectral technique. Width of ESR spectral lines. The width of spectral lines is given by Heisenberg's uncertainty principle, and it is delta E into delta T is equal to h by 2 pi. We know that the energy of electromagnetic radiation is equal to h nu, and therefore delta E can be written as delta h nu into delta T is equal to h by 2 pi. H is constant. On keeping this constant term, Planck's constant, outside the differentiation, we have h delta nu into delta T is equal to h by 2 pi. H will be cancelled out, and we can write delta nu is equal to 1 by 2 pi delta T. It is the expression for line width of a spectral lines. Here, delta nu is the line width in ESR spectrum, and delta T is the average life of electron in the excited spin state. This is line width or bandwidth, and delta T is the average life period of electron in the excited spin state, that is ms is equal to plus half. Now here an assignment has been given. The average life period of the electron in the higher energy spin state is about 10 to the power minus 7 seconds. Then calculate the approximate natural or absolute line width and relative line width of the spectral line in the ESR spectrum. The average life of the electron in the excited spin state, that is ms equals to plus half, is 10 to the power minus 7 seconds. Then we have to calculate natural line width and relative line width of ESR spectral line. Here is the solution. Natural line width is equal to delta nu, and it is given by 1 by 2 pi delta T. 1 by 2, this is the value of pi, and average life of electron in the higher energy spin state is given in the problem 10 to the power minus 7 seconds. On moving this term to the numerator, it becomes 10 to the power 7 per second, and 10 to the power 7 can be written as 10 multiplied by 10 to the power 6 per second divided by 6.28. On dividing 10 by 6.28, we get approximately equal to 1, and therefore the approximate natural line width of ESR spectral line will be 10 to the power 6 per second, and the relative line width will be equal to delta nu by nu. This is the value of delta nu, and we already know that in ESR spectroscopy the frequency of absorbed EMR is about 10 gigahertz, that is 10 to the power 10 per second. On solving it, we get relative line width equals to 10 to the power minus 4. It is a very small quantity, and therefore it is expressed in ppm. ppm line width can be given by delta nu divided by nu multiplied by 10 to the power 6 ppm. Its value is 10 to the power minus 4 multiplied by 10 to the power 6, that is 100 ppm. The relative line width of ESR spectral line is 100 ppm, about 100 ppm. This is very small quantity, part per million. The relative line width is 100 out of 1 million, that is 10 to the power 6. Now we can draw some conclusion from the above problem, from the above assignment. It appears that the ESR lines are quite broad due to large line width. The line width have been calculated to be 10 to the power 6 per second. It appears that the ESR lines should be very broad due to this large value of line width. But in comparison to the frequency of working electromagnetic radiation with frequency 10 to the power 6 per second, this is the frequency of absorbed electromagnetic radiation, and in comparison to this frequency the line width is very small. The relative line width is only about 10 to 100 ppm, and the ESR signals may still be regarded as narrow. Thus, we can say that the ESR spectral lines are narrow. Relaxation process. This is the ground lower energy spin state. Lower energy spin state of electron with ms is equal to minus half, and ms equals to plus half is higher energy spin state. The transition of electron from lower energy spin state to higher energy spin state takes place by absorption of electromagnetic radiation, generally in the microwave region. And once the electron is excited to higher spin state, its average life is about 10 to the power minus 7 seconds. The average life of electron in higher energy spin state is about 10 to the power minus 7 seconds. It immediately comes back to the lower energy spin state. The process of coming the electron from higher energy spin state to lower energy spin state is called relaxation process. This is excitation process, but the process of coming the electron from the higher energy spin state to the lower energy spin state is called relaxation process. The electron in the higher energy spin state can dissipate energy. This excited electron can dissipate energy and can come to the lower energy spin state in two ways. The electron can lose energy and come to the lower energy spin state from the excited state in two ways, and this process is called relaxation process. The first way is a spin-lattice interaction. In this phenomenon, the energy emitted by the electron during its transition from the higher energy spin state to the lower energy spin state is transferred to the lattice. In this phenomenon, the excess energy of the excited electron is transferred to the lattice in which the unpaired electron is present. And this energy appears in the form of translational energy, vibrational energy, or rotational energy of the lattice. The energy emitted by the excited electron during its transition from the higher energy spin state to the lower energy spin state is transferred to the lattice in which the electron is present. and this energy appears in the form of translational energy, vibrational energy, or rotational energy of the lattice, and it is called a spin-lattice interaction. And the second way of a spin relaxation is a spin interaction. In this phenomenon, the energy emitted by the electron during its transition from the higher energy spin state to the lower energy spin state is dissipated, is lost by its interaction with magnetic nuclei, that is nuclei having nuclear spin non-zero or unpaired electrons. The energy emitted by the excited electron during its transition from higher energy spin state to the lower energy spin state is dissipated by the interaction with the nuclei having non-zero nuclear spin or unpaired electrons, and this phenomenon is called a spin interaction. In general, the spin relaxation is more efficient than a spin lattice relaxation because two electrons can come more closer to each other than the electron and nucleus can come closer to each other. Electron can approach each other more closely than electron and nucleus, and this is why the spin relaxation is more efficient, more fast than a spin lattice interaction or relaxation. Thank you for watching the video with concentration. Please like, share and subscribe it so that you may get information regarding my new videos in time. Thank you again.